I'm Tad Hunt, co-founder and CTO of Exablox. I'm going to talk today about our OneBlox file system and our file system technology. So I'm going to start kind of from a top-down features and benefits perspective, and then walk through the a little more detailed technology. The talk is getting a little more technically detailed as it progresses. And so really our products have really three different levels of technology inside the OneBlox. It's really at the top level, it's the protocol stack that enables us to provide SMB and NFS access to the clients.
SMB 2.1?
Yeah, so we do some of the SMB 3 features, but we're not fully SMB 3 compliant yet. So yeah, SMB 2.
Okay.
Distributed file system, which I'll talk about.
Oh, and using you for Hyper-V hosting would be interesting.
Oh yeah, so this product's it's like for 1 gig. You could use it for low performance VMs, but you wouldn't want to put high performance VMs on us today. Distributed file system and distributed object store. These are really the two key technology areas for us in the device. We use open source software for SMB and NFS protocols, and then this is all our intellectual property from here down. And I talked about in copious amounts of detail content addressability and consistent hashing in when we launched at Storage Field Day 3. So I am not going to spend a whole lot of time there. And so like I was saying, distributed file system and distributed object store, these are really our key areas. Across one system in these areas and in our hardware, we've got about 15 patents already, and that number is growing. All right, here's where it starts to get a little more technical. I'm going to drill down into the different components of the stack and what are what do they do and what benefits do they provide. So at the top, we've got our NFS and our SMB stacks, and we use some open source software for that. We have a POSIX-ish file system, and I say ish because we're as POSIX compliant as we need to be in order to enable the workloads. And there's some things that are hard to do in clusters, and so we're maybe not as efficient as a single node NAS at those, but of course the workloads also, that's a much smaller percentage of the workloads too. So we're kind of iterating through these and always making it better. So it's inside the, below the POSIX file system, we've got a cluster manager that actually manages how all these nodes communicate with each other and how do they have a consistent view of the world. And then below that, we've got a consistent hashing ring that on which sit drives, essentially, which is places we're going to land data. And kind of at a very high level, there's a kind of some features that each layer of the stack provides. In the file system layer, obviously the protocols. This is where global namespace across all the devices is. This is where we do provide access to snapshots, and I'll talk about these in more detail. POSIX compatibility, and this is where our file system metadata gets sharded across the cluster. In the distributed object store, this is where the content addressability and the variable sized objects that enable us to do things like billions of objects per node and deduplication and scale out and data protection and encryption at a very fine grain lie. So I'm going to talk at the POSIX-ish file system, our global namespace, through how that actually works under the hood. And there's really about four layers and then kind of 5 or 6 components there. Implement the global namespace is built on top of our Snapshot Manager, and then the whole thing's built on top of our metadata delegation, our lock management, and collections management. So in our system, you can think of collections as shares and export management. And I'll talk about some of the really interesting things that we enable. So we have a technology we call conspiracy that under the hood is what manages our cluster state and generates consensus across the cluster, which we call a ring, to make sure that we can provide those POSIX file system features. It's a bit above and beyond what, say, a NoSQL database with eventual consistency needs to do. We need to actually go a bit further than that. So our collections manager enables per share policies, features, and even on disk layouts. We're able to actually have for say an SMB share for SMB1 or an NFS share for NFS v3, we can actually lay out the data through the entire object store and onto the drives in different ways. And so this enables workload-specific layouts for optimal access for different workloads. Say you're using it for backups, we're going to lay it out in a very efficient way to do a backup because restores are relatively infrequent. So a restore might be a little bit slower, and backup is going to have a very high percentage of dedupe. And then, of course, if you have a bunch of video files and you're doing a primary storage workload with them, you're not going to get so much dedupe, and you might want to lay those out differently. There's essentially no file system limits because all of our file system metadata objects are simply objects in the object store, and it's a scale-out object store, which is the object IDs are basically 160 bits, and so that's more objects than there are electrons in the universe kind of level. So when I say unlimited, it's basically unlimited. It's limited only by how much you can actually deploy. And so this is 7 nodes today, so obviously growing in the future. Shared nothing architecture, so other, as I mentioned before, other folks have differences for, you've got data nodes, you've got metadata servers or controller nodes, and you've got NAS gateways. For us, we build all that functionality into every node so that there is a single failure domain that you have to worry about. You lose a node, or its power goes out or whatever, you just replace the node. You don't have to think about, do I have to scale out my metadata servers differently than I scale out my data servers? And then ring-to-ring replication is all built on this deduplicated content addressable object store and the snapshot by snapshot replication strategy. And so once we take a snapshot, we replicate that snapshot, and it's WAN optimized. It's all deduplicated, and it's depending on how fast your link is to the other data center. That sets your RPO. We're pretty efficient. We're above 90% utilization on that.
The post-process dedupe?
Inline dedupe.
Inline dedupe?
Inline dedupe, yeah. It's another thing that most people can't do.
We may dive far deeper into that, but continue.
Yeah, I'll get into where the deduplication occurs in the system. Beautiful. And a couple of others. So I talked about this thing called conspiracy, and I want to just kind of give you guys a little high-level overview of what is conspiracy and why is it interesting, and why did we build it. So really, any clustered system needs some way to guarantee quorum and make sure essentially that your data is going to be safe, and if a node fails over or the cluster grows, that happens in a very safe and resilient way. And so there's some interesting research that came out of Stanford in 2013 by Diego Ongaro and John Ousterhout. I probably said his name wrong. I only have American phonemes. About this alternative to Paxos. And one of the if you've heard of Paxos, you'll also have heard that it's really, really complicated to understand, and as a result, it's complicated to implement and get right. And there's you got to have big teams and lots of time and lots of tests and lots of expertise to get it right. And so these guys did this research and came up with a much simpler to understand and easier to implement algorithm for being able to manage the cluster state. And so what we did is we started with that paper and we implemented this ourselves. And why did we do that? Is because versus picking up one of these other products that does something similar. In fact, Docker etcd uses the Raft implementation. Zookeeper has a proprietary implementation you may have heard of, and then Google, of course, we can't get our hands on. That's Google's. The differentiators there are, well, first we wrote ours in Python, and then second, why did we do that? Is because we wanted to be able to do a quick, and this is not a core performance piece. We don't exchange much data with this. And so we get dynamic membership changes, which none of the other guys do. Well, none of the other open source guys do. We can run this on some or all of our nodes so that as we make the cluster larger, we can make this more hierarchical. And it's very, very lightweight. And so we were able, under control of that, to do that. Why did we need it, right? And we need some way to manage cluster membership, and I'll talk a little bit more about why we need to do this. When we do consistent hashing, it's all about mapping devices to locations on a consistent hashing ring. And so how do we communicate the information about those devices around the cluster? We use conspiracy for that. I think it's a very appropriate name. This is where persistent configuration, users, groups, shares and exports, and encryption keys get exchanged around the cluster to make sure that all the nodes are in agreement with what the state is. Lock state for POSIX locks and so on. And then what is your persistent state as well? What snapshots have you taken, and how do you name those, and what drives our members, and so on. On the snapshot side, there's really kind of three components there. First, there's the global namespace at the top, and then we have a CDP Snapshot Manager. So CDP is continuous data protection. We do a snapshot every 10 seconds, and that's really an O1 operation or O0 operation, really even because we're a content addressable file system under the hood. In fact, it's hard for us not to snapshot. It's much harder to not snapshot than to snapshot. So all of those snapshots are deduplicated against not only the data in the snapshot and the data across globally the whole cluster, but also all the other snapshots. And so this gets much better deduplication ratios, and it also is global, and it's inline. I forgot to mention that. So you get this, as you're writing, you're already paying the price for all this stuff, and so the performance is constant. You don't have to have a separate landing zone later on that's going to get deduplicated out. Snapshots are actually accessible in your share, and the files and directories in the share actually have the permissions they had at the time the snapshot was taken. So at the root, there's a snapshots folder, and then year, month, day, hour, minute, second. You can drill down to the state of the file system at that point in time. And then, like most CDP systems, we do snapshot thinning. So they start out for primary storage workloads. They say home directories. Typically snapshots are most useful in the last. Somebody usually quickly is like, oh crap, I deleted a file, and they want it back immediately. And so we keep a lot of fine-grained snapshots for the short term, and then as it gets further back in time, we thin them out so they're more granular.
Is that configurable?
Right now it's configurable with either snapshots or no snapshots. Ultimately, we'll make it configurable for more fine-grained kind of what thinning policy do you want. Right now it's a fixed thinning policy. And that covers, the 80% use case.
Sure. But if you've got free capacity, it's not going to thin out until it needs to free up capacity, and it'll start to purge out.
So actually, it always thins out because there's also reasons for compliance, and some folks don't want snapshots, for example, that go beyond a certain date for compliance purposes.
So as I come back to configurable, right?
Well, sure, right. But what we did is we kind of picked a number that seemed it's within most folks around about what most of those companies' compliance with.
Can you share the rough number about when it starts to thin data out?
Do you know what our current?
Yeah, so right now the option is snapshots are on or off on a per share basis, and then within snapshots, first few hours, it's taken every 10 seconds retained, and then it's thinned out to every hour, and then days, week, month, year, and the default is to keep it for 2 years.
Oh, all right. I just wanted to make sure it wasn't like 45 days and like, oh, I really wanted it for 60.
Exactly.
So
yeah,
I'm good with that.
Okay, how do I access the snapshot data? Is it integrated into volume shadow copy for shared folders?
So it's not integrated into that today. What it is at the root of every share, there's a snapshots directory or folder. So in Windows Explorer or Mac Finder or on Unix command line, you just cd
and I can point my
snapshots,
Google appliance at it and index it and
yeah. And then so the other half of snapshots is really this is the driver for replication to a DR site. And so snapshots are replicated asynchronously, and they go snapshot by snapshot, oldest first. And this is when optimized. Again, since snapshots are all deduplicated across all the other snapshots, we only send the deltas every time we do a snapshot. So, if your snapshot was because you updated a PowerPoint, that's going to be a kilobyte, tens of kilobytes, maybe a megabyte sized, snapshot that needs to be replicated across the ring. If you edited a slide, for example, then it's going to be a few kilobytes that goes, and so you'll be up to, your RPO will be very, very close to.
And that snapshot replication schedule can be set up on a CDP, immediately whenever changes occur.
It's always whenever changes.
It's always
occur,
replicated, kind of like
they get added to the queue to send.
Kind of like other products that I won't say
Yep.
for the moment, just
Sure.
who do similar things like that with their CDP backup and what have you.
Yeah, so obviously over time, I think there's a couple of interesting features to build on there. One is, of course, throttling, so we're not going to use the entire WAN bandwidth, and then more schedules, schedule-based stuff, and stuff like that is kind of it's not the deep technology pieces to do. It's the the next kind of iteration to do out there.
Easy to add on after the fact.
Exactly.
Yeah.
And kind of the last thing I want to say about snapshots, I think, which is really, really important, is promotion of a snapshot from read-only to read-write. Say because you experienced a disaster, or you decided to move your application from site A to site B, is really an O1 operation. In computer science terms, this means it basically takes no time. This is like sub-second is what we're talking about here in order to promote a snapshot from read-only to read-write. And by the way, snapshots, as Sean mentioned, are I forgot to say before, are per share. And so you can actually promote, this snapshot of a share to be a read-write. And so, for example, it's a good way that if you want to replicate your state for a bunch of applications, but they all start from the same point, it's very easy to do that. Because you can just, effectively you're cloning the snapshot, but it doesn't, because it's all content addressable, it doesn't actually take anything.
Could you use that then as a distributed file system approach with multiple branch locations and sites?
Yes, you can. Right now, one site will be read-write. All the others, right now, we can only support 2 sites. One site will be read-write, the other site will be read-only, but it will be exported so your clients can browse.
Okay.
Promotion is something you do through one system, and so from a client perspective, nothing changes. It's all of a sudden they just don't get write errors, if it gets promoted, and so that's under your control as the admin.
So it can't be like a full DFSR, but at least it gives you
Correct.
the ability to half of it at least.
Our primary use case for this today, by the way, is for DR, and so it tends to be, you only want to promote the other site once.
When the former site is dead. Okay, cool.
And multi-master replication is hard.
And it's hard, and so we thought we'd, iterate our way there.
You covered, but can you fail back if you were to promote one
Yes.
site?
Yeah. So we call it toggling. You can toggle which sites read-write, and then after a failure, you can promote. And so toggling is consistent with the snapshots. So we'll wait, the other site will become primary. We'll stop writes on the site that was read-write. We'll sync all the writes in progress. And once the other site has all the writes, it'll become read-write. And so it's consistent. You won't lose anything in transit. Promotion is obviously after a failure, so you might lose whatever hasn't been synced.
Sure.
It's asynchronous. Right?
Yeah, but because it's all deduped and we've got hashes on everything, the resync is easier.
Well, in other solutions, the resync would consist of destroying the source that you then
And transferring all your data back.
Exactly.
Yes, in fact, I can think of a dozen solutions that do that.
And that, because it's all content addressable object store, we send a list of objects, essentially.
And it says already exists, so don't.
Yeah. So on a snapshot by snapshot basis, we send just the list of objects. Here's the objects in the snapshot, and then the other end comes back with, here's the ones I don't have.
Yeah, because there's nothing like trying to replicate 50 terabytes of data over a
Exactly.
DSL line.
And we do it in the namespace form as well. So if we know that a whole subtree's been transferred, we don't actually bother to visit all the sub-objects under there.
Okay.
So it actually is even more efficient because of that.